Hello learners, I am Dr. R.B. Malati, Assistant Professor, Chhattisgarh Swami Vivekanand Technical University, Bhilai. I welcome you all again to the course Essentials of Surveying Application Techniques. In the previous lecture, several essential topics were covered and that sets the stage for today's lecture on linear measurements. In the last session, we discussed on plans and maps, defining their roles and differences. The concept of scale was also given to you, discussing its importance in surveying. Errors caused by using the wrong scale was examined, highlighting how inaccuracies can arise from incorrect scaling. Additionally, the concept of a shrunk scale was covered, where the scale on a map or the plan is reduced compared to the actual measurements. With this background, let us look into measuring distance. There are two main ways to figure out how far apart two points are on the surface of the earth. That is the direct method and the computative method. Let us look in a way that is easy to understand. First is direct method, and this is a hands-on approach. Think of a construction worker measuring the length of a wall using a measuring tape. They extend the tape from one end of the wall to the other and take the exact measurement. That is direct measurement, as simple as that. Now, the next one, that is computative measurement. This is where things get a bit more mathematical. Instead of physically measuring the distance, we calculate it. This method is used in techniques like tachymetry and triangulation. Simply visualize you are a surveyor working on a large field. Instead of walking across the entire field with a tape measure, you use a tool called a theodolite to measure angles from two known points. With a bit of math, you can calculate the distance between 2 points without stepping on the area between them. Each method has its own limits on accuracy. So let us explore a bit more under the heading Methods of Direct Measurements. Here are the common ones. First come the chains. This is one of the oldest methods. Chains are composed of links and are used to measure distance in fields. Then we have tapes. These are modern methods and can be made of materials like steel or fiberglass. Tapes are used for measuring shorter distance with higher precision. Lastly, we have electronic distance measurement. This is a high-tech method where devices use electromagnetic waves to measure distance with extreme accuracy. These days, the construction projects often use EDM devices to ensure the foundation of buildings are laid out with perfect precision. So the bottom line here is, each of these methods comes with its own sets of pros and cons. Chains are great for rough measurement over long distance, and tapes offer better precision for shorter distance. And EDM devices provide the highest accuracy but can be more complex and expensive. Okay, now let us learn about the tools. We will cover the different types of tapes first, and I will try to use some easy example to help you understand each one. First is tapes. Depending on what they are made of, tapes are classified into four main types: cloth or linen tape, metallic tape, steel tape and invert tape. Let us see one by one. Before that, let us understand one principle here. Think of chain surveying like putting together a big flat jigsaw puzzle. The basic idea is to break down the area into a bunch of triangles. Why triangles? Because a triangle is the simplest shape you can work with when it comes to plotting land accurately. If you know the lengths of all the three sides of the triangle, you can plot it on a map without needing to worry about angles. This is why chain surveying lies on creating a network of triangles to cover the area. So, getting back to our classification, first we have the cloth or linen tape. These tapes are made from closely woven linen coated with varnish to resist moisture. They usually range from 10 to 30 meter. Repeat, they usually range from 10 to 30 meter in length and are about 12 to 15 millimeter wide. One end of the tape has a ring included in its total length. The disadvantage here is these tapes can get pretty frustrating because they twist and tangle easily. So next we have metallic tape, and this is a linen tape reinforced with brass or copper wires to prevent stretching or twisting. These wires are hidden so you can't see them at all. They come in various lengths, but 20 and 30 meter tapes are the most common one. They are great for accurate measurement, especially for taking offsets distance in chain surveying. Then comes the steel tape. The steel tapes offer higher accuracy than cloth or metallic tapes. They are light strips 6 to 10 millimeter wide with precise graduations. They usually come in the length of 10, 20, 30 or 50 meter and have a grass ring at the end. Let us say you are measuring out the foundation for your playground. And lastly, we have invert tape. Made from an alloy of nickel 36% and steel 64%, these tapes have a very low coefficient of thermal expansion, meaning they don't expand or contract much with temperature changes. They are 6 millimeter wide and comes in the length of 30, 50 or 100 meter and are used mainly for high precision measurements. If you are doing good work like measuring the baseline for a scientific survey, you had to use an invert tape. However, they are expensive, prone to deformation, require careful handling. Let us move to the steel bands. Now, you picturize this. You have got a steel band and it is basically a long ribbon of steel about 20 to 30 meter long and 16 millimeter wide with a brass rail handle at each end. Here is how it is marked. Every 0.2 meter there is a brass strut. These struts are like tiny mile markers with numbers at every meter. The first and last bits are divided into centimeters and millimeters for fine measurement. On one side you have got the whole metric family, meters, decimeter and centimeter, and on the other side it is all about the 0.2 meter lengths. Yes, done. Now let us talk about why steel bands are suitable choice. First comes the accuracy. Whenever accurate measurements are required, you have to go for steel band. Next is a lightweight. It is lighter than carrying a chain, of course. Then is a stability. Unlike chains that can stretch or shrink over time, the steel band stays the same length, keeping your measurement consistent. Then fragility. It is bit delicate and in case it is broken, it cannot be repaired in the field. Next is the maintenance. It must be protected from rust by frequent cleaning and oiling. And finally, the visibility. It is not as easy as you read your chain. So next come in the surveying, chains. Chains are pretty essential tool and there are a few types you will come across. First is the gunter's chain. This one is 66 feet long with 100 links, each link measuring 0.66 feet. Next is the engineer's chain. This is a bit longer, about 100 feet and also divided into 100 links with each link being 1 foot. Then is a metric chain. These comes in 20 or 30 meter and are divided into 100 or 150 links and each link here measures 20 centimeter. Now let us look into the metric chain a bit more. These are usually made from pieces of galvanized mild steel wire which is 4 mm in diameter. The ends of each link are bent into loops and connected by 3 oval shaped rings, making the chain flexible. The ends have brass handles with shell joints, so you can turn the chain around without its twisting. The length is measured from outside of one handle to the outside of the other. Now coming to the links, they are connected by open joints, but in good quality chains, they are welded to keep the length accurate despite stretching. For quick and easy reading, metallic tags are fixed at important points like 5 meter, 10 meter, 15 meter and 20 meter. And according to Indian standard IS 149-1956, these chains are calibrated in meters and smaller subdivisions. They usually have small brass rings every meter except at key points like 5 meter, 10 meter, where tallies are fixed. The handles have grooves to hold arrows correctly and the length is marked on the handle for easy identification. Now these chains are good for some things but not so much for others. Let us understand this under suitability of chain. Chains tend to change length with use, so they are best for ordinary work. Length can shorten due to bending links or lengthen by flattening rings. Chains are heavy and sag when suspended. They are great for rough usage. And this chain over time, the links of the chain might bend, shortening its length, or they might stretch, lengthening it. You need to check the chain's length before you start and your day's work and frequently after to ensure the accurate measurement. Make sure the links aren't bent, the openings aren't too wide and there is no mud on them. The rings should be circular. A small test for this. For accurate measurement, a tension of 8 kg, that is 78.5 Newton, is applied and compared against a certified steel band standardized at 20 degrees centigrade. Each meter length should be accurate within plus or minus 2 millimeter and the overall length should be accurate within plus or 5 millimeter for 20 meter chain and plus or minus 8 millimeter for 30 meter chain. Now, let us look into adjusting a chain in the field. If the chain is found to be too long, you can adjust it by closing the open joint of the rings, reshaping the elongated rings, removing one or more small circular rings, replacing worn out rings. And if the chain is too short, you can straighten bent links, flatten circular rings, replace small rings with the bigger ones and insert additional circular rings. Make sure adjustments are done symmetrically to keep measurements consistent across different parts of the chain. Now let us understand the instrument used for marking the survey stations. When you are working in soft ground, wooden pegs are the way to go. These pegs are usually 40 to 60 cm long and about 4 to 5 cm square. Drive them into the ground so they stick out about 5 cm above the surface. And these pegs can come in wooden pegs, iron pegs. Wooden pegs, they are basic markers. They are typically 2.5 cm square and 15 cm deep. Just plant them where you need to mark a survey station. If it is iron pegs, if you are dealing with harder ground, this is a choice. They are tougher and will hold better. Next is the ranging rod. These rods help mark station positions while you are ranging a line. Made from well-seasoned teak or deodar timber, they come in lengths of 2 meter or 3 meter with a 3 meter diameter. And they are divided into 0.2 meter parts and have a cross shoe at the bottom for stability. They are usually painted in alternating black and white sections for visibility. Next, the ranging poles. Think of these as a beefire ranging rods. They are heavier, 4 meter to 6 meter long and perfect for ranging very long lines in uneven terrain. Next is the offset rods. Similar to ranging rods, these are generally 3 meter long, divided into 0.2 meter parts. The top has an open hook for handling chains through obstructions and there are vertical slots eye level for aligning offset lines and measuring short offsets. Next is the plumb bob. This handy tool is used to transfer the end points of the chain onto the ground when you are measuring distance in hilly areas. It is also great for checking the verticality of ranging poles, rods or leveling staves. So, those are the main tools you will use for marking survey station. Let us now understand how about the process of ranging a line. Ranging a line is all about marking intermediate points on a survey line between two stations so that you can measure the distance accurately. If the line is short, you can see the end station clearly, you can just lay the chain straight. But if the line is long or the end station is hidden because of hilly terrain, you need to mark several points with ranging rods like A, B, C, D, etc. along the line before you start measuring the distance between the points capital A and B. So, how do you do this ranging? You can range a line by eye estimation using a line ranger or a theodolite. Ranging is classified into two main types, direct and indirect. Direct ranging. Direct ranging is when you place ranging rods along the chain line by directly observing from either end station. Here is how you do it. Set up ranging rods, that is, you place ranging rods or poles vertically at each end of the line. Then position yourself, that is, you stand about 2 meters behind the ranging rod at the beginning of the line. Next, direct the assistant. You ask your assistant to hold the ranging rod at arm's length where the intermediate station is to be placed. Then align the rod. You direct the assistant to move the rod left or right until all three ranging rods are in straight line. Next is double check. Stoop down and sight over the lower ends of the rods to avoid errors due to non-vertical rods. Next, fix the rods. Once aligned, signal your assistant to fix the ranging rod in place. Use clear signals to direct the assistant, and if they are so far away, use a handkerchief for signaling. Next, using a line ranger. A line ranger is a small reflecting instrument for fixing intermediate points on a chain line. It consists of two right-angled isosceles triangular prisms stacked on top of each other. So, here are the steps. Step 1. Stand near the point C. That is, position yourself approximately in a line near point C and hold the line ranger at eye level. Next, absorb light from A. The light from A enters the upper prism, reflects off the hypotenuse and enters your eye at right angles to AB. Next, observe light from B. The light from B enters the lower prism, reflects off its hypotenuse and enters your eye at right angle to the line BA. Check the images. That is, look at the images of the ranging rods A and B in the upper and lower prism simultaneously. Next, adjust position. If point C isn't in line with AB, the images will be separated. So, move the instrument back and forth until the images are aligned in the same vertical line. Next, fix point C. Center of the instrument will mark point C on the line AB for you. Moving to the indirect ranging. Indirect ranging is used when the end stations are invisible from each other. You place intermediate ranging rods by interpolation, reciprocal ranging or running an auxiliary line. Use indirect ranging in these situations when there is a raised ground obstruction or when there is a large distance. Now, let us look into a chaining a line. Imagine you and your friend are working together. For this job, you both have specific roles. One of you is a leader and the other is a follower. So, the leader, the first step for him is drag the chain forward. It means you move ahead dragging the chain behind you. Step 2 is insert an arrow, that is, place an arrow at the end of each chain length and also follow the instruction. That is, listen to and follow the follower's directions here. Now comes the follower step. For him, the step 1 is direct the leader. Make sure the leader stays in line with the ranging rod. Then carry the rear end. Repeat, then carry the rear end. Ensure the chain stays above the ground and doesn't snag. Then finally pick up arrows, collect the arrows that the leader inserts. So, the method of changing is executed this way. Starting off, the follower holds chain's handle at the start point, let us say peg A. The leader grabs the other end and heads towards the first point, aligning with the ranging rod. Then the leader, holding 10 arrows in one hand and the chain handle in the other, walks forward, that is, setting the chain. When the leader reaches the end of the chain length, they place a ranging rod vertically and wait for the follower's signal. Now comes the aligning the chain. The follower directs the leader using hand signals to move left or right until they are perfectly in line. Once aligned, the leader stretches the chain, places an arrow at the chain's end and moves on. Then marking the spot, the leader places the arrow into the ground to mark the end of the chain length. If the ground is hard, the leader can scratch an arrow with an arrow or chalk and place the arrow there. Finally, continuing the chain, the follower moves up, grabs the last fixed arrow and yells chain to alert the leader that they have reached a full chain length. The process repeats. The follower holds the chain handle at the last arrow and the leader moves forward again. So here are some of the golden rules to remember. The chain is too long, your measured distance will be shorter, and if the chain is too short, your measured distance will be longer. Now let us understand how to adjust your measurement. First comes the true length of a line. Formula for this is faulty chain length divided by standard chain length into measured length. The example here is, suppose you measure a line and it is 100 meter with a chain that is stretched to 21 meter instead of standard 20 meter. The true length will be 21 by 20 into 100 is equal to 105 meter. So the real length of your line is 105 meter and not the 100 meter you measured. Huge variation, right? Next is the true area of a plot. True area of the plot is given by faulty chain length divided by standard chain length, the whole squared by measured area. An example here, if you measure the area of the plot as 500 square meters with the same 21 meter chain, the true area will be 21 by 20 the whole square multiplied by 500, which gives 551.25 square meter. This shows the real area of the plot is 551.25 square meter and not 500 square meter. Next, the true volume of an excavation. Formula here is faulty chain length divided by standard chain length, the whole cube multiplied by measured volume. An example for you is, if you measure the volume of an excavation as 1000 cubic meter with the same faulty chain, the total volume will be 21 by 20 the whole cube multiplied by 1000, which comes to 1157.63 cubic meter. So the real volume is around 1157.63 cubic meter and not 1000 cubic meter. The handy hint here is, think of it like balancing act. The product of the correct length and correct chain length should equal to product of the incorrect length and incorrect chain length. So whenever you suspect your chain might be wrong, just remember these simple adjustments. Let us take a look how to find the true length of a survey line when your chain isn't quite right. Here is an example to make it clear for you. Example, the length of a survey line measured with a 30 meter chain was found to be 981.6 meter. When the chain was compared with the standard chain, it was found to be 0.20 meter too long. Find the true length of the survey line. The solution is, let us first identify the variables, that is L dash, which is the length of the faulty chain, is 30.20 meter. L, which is standard chain length, is 30 meter. Measured length given is 981.6 meter. So using the formula, true length of the line is equal to L dash by L into measured length of the line. We can calculate the true length as 988.14 meter. So the true length of your surveyor line is approximately 988.14 meter and not 981.6 meter that you measured. Done. Let us move to the next topic, that is types of errors in chaining. Errors in chaining may be of two types. First is the cumulative error, which can be further divided into positive and negative. These errors keep piling up in one direction, make your measurement consistently wrong. When we look into this positive cumulative error, these makes your measurement longer than that it should be. And the causes for it are, the chain is too short, ignoring slope correction, not correcting for the sag, and poor alignment, windy condition. Next, we have the negative cumulative error. These make up your measurement shorter. They often occurs when chain is shorter than the standard. So, the bottom line is cumulative errors grows with the length of the line. Though they can be large, you can correct them by applying the necessary adjustment. So, let us look into the second type, that is compensate cumulative errors. Compensating errors can go either way and tend to balance each other, making them harder to pinpoint, and these are the causes: incorrect chain handling, uneven calibration, and poor plumbing. Bottom line here is compensating errors are proportional to the length of the line but are typically smaller compared to the cumulative error. They can't be easily corrected because their nature is harder to determine. So, to ensure precise measurement, we need to adjust for various factors that can affect the accuracy of measurement. So, the factors are correction for standard length. Next is correction for alignment. Third is correction for slope. Fourth is correction for tension. And fifth is correction for temperature. And sixth is correction for sag. And the seventh is reduction to mean sea level. So, by applying these corrections, you can ensure that your measurements are as accurate as possible regardless of the conditions of equipment that you are using. So, there we finish our lecture. Summary here is, in today's lecture on measuring distance in surveying under the heading linear measurements, we have covered direct and computative methods, various tools and their uses, and how to handle errors and make necessary corrections. Remember to choose the right tool for your project and adjust your measurements to ensure good accuracy. Happy learning. Good day.